Alright, in stellar metamorphosis, we have stars. I know you guys love watching me draw these circles. I'm getting better and better at it, can you tell? We have stars that have iron cores. Now, depending on the radius of this, or I should say diameter, if you cut in half, that would be the radius, D. Depending on how wide this is, will determine how long it took for it to form. In other words, if you have a core which is pretty big, and then you have a core which is middle-sized, and you have a core which is small, and you have a really, really small core like this. Okay? As a rule of thumb, the bigger you get, the older it is, or the longer it took to form. This reasoning is natural philosophy. You have large core taking longer to form because, well, it's larger. Smaller core doesn't take that long to form. So progressively, if you have a star with a small core versus a star with a larger core and all the way up, it means this formed a lot quicker than this formed quicker than this, and then this formed quicker than this. Basic rule of thumb. And if you'll notice, I think I remember this, Mercury has a disproportionately large core, and Earth has a core roughly the same size. So you have Earth's core, but Earth is a lot bigger, meaning Mercury and Earth, their cores took about the same time to form. This also means that over time, bombardment from meteorites and impacts and things like that has literally ripped away its outer layers until it exposes this core. That means, as well, since these are the same size, and this clearly is a lot thinner, that Mercury is a whole hell of a lot older than the Earth. And it also means we should find evidence of this age with a whole crap load of hitting from strikes, from asteroids and other objects. And we're in luck, we do. The Earth has a liquid mantle, okay? That means if something hits the Earth, boom, swallows it up, repairs it, depending on its size. A really big one would just go, you know, and then the Earth would swallow it up. And it would be heavy right here, there would be a gravitational anomaly, depending on the composition of whatever got hit, or whatever it was that hit the Earth. This is very important, because to establishment science, they say Mercury and Earth formed at the same time, but they did not form at the same time. They are completely mutually exclusive of each other, and they were both adopted by the Sun when the Sun came into the vicinity. Back to the original age of the iron core, and why I mentioned natural philosophy. Here, let's use blue. Okay, say you have a tree, okay? This is going to be a really crappy tree drawing, so bear with me. You have a tree, okay? If you slice it, what you'll have is rings. Just like this. Okay? Now you can count the rings to determine how old the tree is, because those are the yearly cycles that the tree goes through. Cold, hot, you know, for the winter and summer months. And that's basically how we tell how old a tree is. Now, if you have a tree that has very few rings, maybe 3 or 4, it's young. It's younger. And this is 15 years, this would be 5 years, okay? Now, the rate at which that grows, I'm not too familiar with biology, but that's basically how it works, how you can determine how old the tree is. Now, when you want to age the core of a star, what you would have to do is figure out the rate at which material deposits itself onto the core internally inside the star. So pretend there's a big atmosphere here, and it's constantly depositing that iron and nickel in the center of the star. Okay? How exactly would you determine the rate at which this material is deposited? Because that would tell you how old this thing really is. You need to know the rate of deposition, and you need to know the size of the core. This would set a lower limit on the age of the star. Now, this is very, very important, because if you can determine how old the core is by determining the rate of deposition of the iron and nickel, and you determine its size, it means radiometric dating of the crust, which is the last object, or last thing to form on a star. As you well know, it deposits. The crust is the last thing to form. Okay? So if they if they date this crust, and they say it's 3.5 billion, and we all know through stellar metamorphosis that this is the last thing to form, it literally means that this object is probably much older than 3.5 billion, because this is the last, and this is the first thing to form. So without even radiometrically dating it, we can determine how old a star really is. Now, I don't know if this is an exact thing, this is kind of new, but I guarantee you, you're not going to see this anywhere on the internet, except for here. If anybody wants to comment below, go ahead, but that's basically all you need to do.